Okay, so now let's consider a simpler example based on the previous theory. So let's consider two-dimensional flow over some periodical domain. So we have 2D periodic domain. And we have incompressible flow, like for example water. So flow of water, incompressible fluid, and non-divergent, which is which means that divergence of velocity equals to 0, and this follows from continuity equation. So in that case, for continuity equation, because d rho dt equals to 0, so rho is constant, then this term will drop out, and also rho can be taken away from inside of divergence. So our continuity equation will have very simple form: du dx plus dv dy equals to 0. So this is non-divergent flow. And the equation for quantity phi will be written simply as d phi dt plus u d phi dx plus v d phi dy equals to 0. We have no sources or sinks, so q equals to 0. And so this one is a directive form, but we will use a flux form, which is d phi dt plus d dx u phi plus d dy v phi equals to 0. So this is flux form. So now we consider conservation. So conservation of phi, the conservation of phi is easy to show using flux form as we did before. So if we integrate over some volume, then we will have that integral of phi dx dy over our periodic domain, and these terms will cancel out because integral of derivatives will have over periodic domain will vanish. So total integral over that area, over that domain of phi equals to 0. So it's, I mean, rate of change ddt. So it's conservation of total phi. Now how about conservation of phi square, which is kind of analog of kinetic energy? So some conservation of variance of phi. So in case if phi is velocity component, so for 3 velocity components, so each of them, if each of them conserved, or quadratic quantity is conserved, then its conservation of kinetic energy is assured. So conservation of variance is easiest to show using this equation. But generally, as we showed before, so this equation is just d phi dt. So any function of phi is also conserved, as we showed before in one of the lectures. So if you have some arbitrary function of phi, then df dt equals to df d phi dt, and d phi dt in our case equals to 0, so it's equivalent to 0. So any function of phi is also conserved if phi is conserved along the trajectory. So if phi is just a function of phi, say square, so let phi of phi equal to phi square, then phi square should also conserve. along the trajectory. So for that, then we have equivalent equation of in flux form and from that, similar how we because it's in flux form, so we can basically we see that the same is true, the conservation of total variance in a domain also in periodic domain is also assured. It's ddt integral phi square dx dy equals to 0. So kinetic energy is also conserved, or any other function is conserved. So for example, you may have logarithm of phi in a domain. So if it conserved along the any streamline, like a total derivative, then total integral of that logarithm of phi will be constant. It's not going to change. Okay, so nice. So now we need to, this is based on analytical expressions or calculus equations. So now how about finite difference equations? Do we have similar conservation properties? So let's consider that. So let's just copy it here. Have equation like this. So we consider finite difference representation of these two equations. Well, let's consider a simple case when we have rectangular grid. So we have index I plus 1, I minus 1, so this is in x direction. And in y direction we have indices j plus 1, j minus 1. So coordinate of this point, index of this point is ij, so it's ij, and and all quantities are defined in the same point. So it's like Arakawa A-type grid. So now let's approximate our advection equation with second order accuracy using centered differences. And we won't approximate, for the reasons I told before, time derivative. So we'll assume that time derivative still remains analytical. So we have the following scheme. Scheme 1. As d phi ij dt plus u I plus 1 j phi I plus 1 j minus u I minus 1 j times phi I minus 1 j. So it's basically this minus this to approximate this term, divided by 2 delta x, this is delta x, delta y, plus Vij plus 1, phi ij plus 1, minus Vij minus 1, phi ij minus 1, divided by 2 delta x y equals to 0. So this is second order centered differences. So now let's see, do we have conservation of phi, for total phi? So in case of velocity it would be conservation of momentum. And in terms of if phi is say temperature, it's just conservation of total temperature, or if it's So in a way, it's like conservation of the total internal energy of the system. So so what we have here, let's sum, so it's dt sum over I and j, so it's double summation index of indices I and j. And here we have u I plus 1 j phi I plus 1, so it's this is not correct. It's sum ij phi ij, and let's multiply it by 2 delta x and 2 delta y, so it's basic conservation over this square, so that we don't have to and we assume that delta x equals to delta y, so we don't have to then carry it all around for delta x delta y. So we multiply this whole equation by 4 delta x delta y, then we cancel all these denominators. So plus sum ij, we have this ui plus 1j phi I plus 1j minus ui minus 1j phi I minus 1j plus vij plus 1 phi ij plus 1 minus vij minus 1 phi ij minus 1. So let's consider this sum. It's very similar. We have periodic domain, so we can, over periodic domain with all the summations, we can add or subtract 1, 2 indices when they're under the summation sign. It's not going to change anything. So let's do that. Let's add 2 to these indices. So what we get? It's plus 1, plus 1. We can do it to separate terms because each of those terms is actually has summation sign. So from that we see that these terms cancel, and here we also add 2 to j index, and we have identical expressions. So this guy will disappear. And from that we have conservation of total phi ij. So yeah, this is, please make sure that you understand how it's done. So basically the idea is very simple. Fluxes, this is kind of in flux form. You have this flux, it's defined here. For this quantity in here, this flux defined in here. But then for the quantity which is here, we have the same flux here. So when you add this plus this flux comes with a plus sign, and for this flux it comes with a minus sign. So when you add those two quantities, this flux will just cancel out. So that's why flux form is nice to have, because it allows you to cancel all this. If you sum, all these fluxes will cancel out. Of course, you need to make sure that your coefficients are right. So in this case, when we have delta x delta y, we just can write it's just like that. So we have proven that our scheme like this, it conserves total phi, or total first moment of momentum of the system. Nice. So now, more complicated case. Does it conserve quadratic quantity or variance of phi or kinetic energy? Let's see. So for that, we take our scheme, this scheme, and we multiply it by phi ij. So we have ddt sum k k of phi ij squared over 2 plus, so, and we of course again multiply it by 4 delta x delta y, not to carry it around. So plus sum ij. So let's see. We have u I plus 1j, phi I plus 1j, phi ij. We multiply by ij, phi ij, each of those terms, minus u I minus 1j, phi I minus 1j, phi ij, plus v ij plus 1, phi I j plus 1 phi ij, and minus v I j minus 1 phi ij, phi j minus 1 phi ij. So let's see, can we use our trick to cancel those guys? So if you add so let's see, we have this double term phi phi here, so let's make them look like similar. So we add 1 to each of to this index 1 to I index. So we have with I, this guy disappears, this guy disappears, and this will become I plus 1j. And here we add j to this 1 to j index here. So this one is like that, it's like that, and this j plus 1. So it can be then written as sum ij, phi I plus 1, 1j phi ij, u I plus 1j minus u ij, plus phi I j plus 1 phi ij, v ij plus 1 minus v ij. Well, as we saw like in our first burger equation example, it's very similar terms. You cannot really, so these phi's are arbitrary, right? They don't depend on u, let's say. So it can be any numbers here. And u's can be any numbers, arbitrary numbers, so there is no way they cancel. It's not, there is no symmetry here. So what we conclude, that this guy is not equal to 0 when summed, so that d dt of sum k of phi square ij over 2 is not equal to 0. So there is no conservation of energy by this scheme. So if you have some nonlinear instability, so nonlinear process, this scheme may blow up easily, because it doesn't, even though it preserves momentum of first moment, but it doesn't preserve quadratic quantity. And quadratic means again that energy supply is limited, because conservation of momentum does not exclude very large numbers. You have very large positive numbers and very large negative numbers. So that the total can be 0, but it's still instability, while you have again a positive conservation of quadratic numbers. Quadratic, they're always positive, so if sum of all positive numbers should be preserved, then regardless what you do, you cannot exceed that number. So that means that energy is limited and instability is not going to happen. So that's why it's important to preserve quadratic quantity by this scheme. So this scheme is not good for that. Let's modify the scheme a little bit. So by the following. So let's consider scheme number 2. let's consider the following scheme. We have, let's average u's in here. So this is going to be ui plus 1 half j. Here we're going to have ui minus 1 half j. Here we have v I j plus 1 half. So 1 half means just in the middle. Here v I j minus 1 half. So we consider the following scheme. And also we average phi's here too, to the middle. So we consider the following scheme. It's u I plus 1 half j phi I plus 1 half j minus u I 1 minus 1 half j phi I minus 1 half j divided by delta x. Here's the distance between them is just delta x, and plus v ij plus 1 half phi ij plus 1 half minus v ij plus minus 1 half phi ij minus 1 half divided by delta y equals to 0. So u I plus minus 1 half equals just average u I plus minus 1. So this is how you define it, similar for phi. Just average those values on a grid. You just average them to the middle of the grid, and then use those averages to compute those divergences or those fluxes. Yeah. So let's see, does it conserve momentum or first moment, the total, the sum of all phi's over the grid? So we have ddt sum ij phi ij equals to what, times 4, or in this case just delta x delta y, equals, we have sum ij u I plus 1 half phi I plus 1 half j minus u I minus 1 half j phi I minus 1 half j plus v ij plus 1 half phi ij plus 1 half minus v ij minus 1 half phi ij minus 1 half. So now we add 1 to both, to this say term, to index I. So we have plus 1 half plus 1 half, and here we add 1 to index j, plus 1 half plus. And then you see that they will cancel. Of course, it's just because for this variable here, it's this flux minus this flux. For variable here, it's this flux minus this flux. So again, this flux for this variable comes with plus. This flux, this flux for this variable comes with plus, and this flux for this variable here, this flux, sorry. So for this variable, this flux comes with plus, and for this variable phi in the grid point, this flux comes with minus, because it's this minus this. So when you add those two guys, this flux just will cancel. This is basically what it means. And the same in y direction. So everything is cancels out. So as long as you wrote something in flux form, your derivatives, you're basically sure that your quantity is preserved. basically automatic. So as long as you wrote it like that, one flux minus another flux, regardless how you represent this flux, you can represent in this case by averages, or previously we didn't even average anything. It's still, as long as you do it in the flux form consistently, and you use the same flux on the left boundary the same as on the right boundary and so on, your summation will cancel all those fluxes out. So that's why flux form always basically assures conservation of the quantity itself that is predicted. But how about quadratic quantity? That's a different story, right? We saw already that before that we preserved quantity itself, phi itself, the sum of it, but we didn't preserve quadratic square of that quantity summarized over the whole domain. So let's see. So for this case, this one is 0. Great, so it's conserved. So this thing is 0. Conservation of total phi. It doesn't change with time. So now let's see if this scheme preserves quadratic quantities. For that, we need to multiply it by phi ij, and in that case we cannot just simply do that. We need to actually substitute this definitions of halfway quantities, average quantities, and then multiply the resultant equation by phi ij. So let's do that. Let's free some space here. So we use this definition. So what we have, d dt sum ij phi ij squared over 2 times delta x delta y plus sum ij. So here we just substitute this and just write it explicitly. So and then multiply those terms. So what we have, we have u I. So here it's I j j j u I j. Actually, we only need to do it for phi, so we preserve I plus 1/2 j, and we just use this average, explicit expression for average, so we have I plus 1 j times phi I j plus u I plus 1 j phi I j squared minus u I minus 1 j phi I minus 1 j phi I j minus u I minus 1/2 j phi I j squared blue plus, so we took care of these guys, v I j plus 1/2 phi I j plus 1 phi I j plus v I j plus 1/2 phi I j squared minus v I j minus 1/2 phi I j minus 1 phi I j minus v I j minus 1/2 phi I j squared. Oh, messy. Lots of terms. Okay, now let's see. So we're not gonna touch terms with phi I j squared, but right for now. But let's deal with these terms that don't have phi I j squared. So how about this term and this term? So let's add 1 to all I indices here. We need to add to all of them in this particular term. So we have plus So I minus 1 plus 1 just becomes I, and here we have I plus 1j. So if we look, this term and this term, they're identical, so they will cancel each other. So this term and this term will cancel. Now this term is similar, so add 1 to j index for this term. So we have plus 1/2, here we have ij, and here j plus 1. So now if you look, these terms are now identical and they have different sign, so they will cancel each other out. So what is left, those we cannot do, cancel like that, but they all have ij squared in them. So that ij squared can be taken out outside, phi ij squared times u I plus 1/2 j minus u I minus 1/2 j plus v I j plus 1/2 minus v I j minus 1/2. But remember, we actually, all these terms used to be divided by delta x and delta y. So basically, what is this? This is finite difference representation of this continuity or non-divergence equation. It's, well, if you divide it by delta x and delta y, and because we just multiply it and we assume that they is the same, but if we didn't do that, preserve that, it wouldn't change actually. Then you would see it probably easier. Well, maybe I should do that. Remember? So they would look like that if we didn't do that. And this is just finite difference approximation of this u minus u, u minus u, v minus v. And so if our velocity on our grid have this property, that is, continuity equation is valid on an infinite difference sense, then this term will drop out. It's not only just because of summation, but because we didn't actually change any indices. It's just each of those terms will be equal to 0. And so the summation will be equal to 0, and the whole thing is equal to 0. So as long as you have continuity equation valid on your finite difference grid, phi squared will be conserved for this scheme. We didn't have those terms in our previous schemes, so we couldn't do that in our previous scheme. Because we did, first of all, we didn't have the same factor phi ij squared. We have like phi I plus 1j times phi ij, so we couldn't do anything like that. So in that case, it's conserved. So how to make sure that first of all, this ui plus 1j minus ui minus j, if we remember definition of those guys, you see that this ij would cancel. So this one is equivalent to the scheme ui plus 1 j minus ui minus 1j divided by 2 delta x plus vi j plus 1 minus vi j minus 1 divided by 2 delta y equal to 0. So a set of difference representation of continuity equation is velocity on a grid, this velocity minus this velocity plus this velocity minus this velocity. So as long as this is valid, then we will preserve. If it's not, if our flow is divergent, so this is not true, then there is no way to preserve quadratic. There is no way to preserve quadratic quantities, but still momentum would still be preserved regardless of that, because we remember we didn't need that condition for momentum, for just phi quantity. But to preserve squares, you actually need a continuity equation to be valid. So this is actually scheme 2. This scheme 2 does preserve squared quantities that are transported, provided continuity equation is valid. So how you make sure that continuity equation is valid, that's we're going to talk about in some other lecture. But so because you actually, if you specify U and V, it's one thing, but usually in the model, you also you make prognostic equation for U and V's. So your prognostic equation should make sure that your U and V, that the velocity field is non-divergent. And we will talk about that when we'll talk about so-called elliptic equations. For now, we're kind of not talking how you actually make sure that it's actually true. But as long as it's true, there is no problem with conserving quadratic quantity. So you see that you have to be very careful with the choice of approximation of your fluxes in this case. If you're careless, you will generate some artificial kinetic energy without even knowing it, and this scheme basically is almost impossible to blow up. Well, using as long as it's using nonlinear mechanism. Of course, it can still blow up if it's linearly unstable. Remember that current stability criterion, if they violated this scheme, will blow up anyway, because that's a completely different mechanism. But nonlinear instability won't be able to blow it up because there is no energy available for the scheme to, say, 2 and 4 delta x ways to grow. And that's via a nonlinear instability mechanism. So this scheme would be much more stable. It still may generate noise, but it won't become unstable. Finally, I would like to finish this lecture on conservation by some comments on conservation properties of the time derivative. So far in our analysis, we always assume that the time derivative is continuous, but in reality, of course, in the model, it would be itself approximated by some finite differences. So, for example, if our time derivative approximated using forward in time scheme, one step forward in time, n plus 1 minus phi n divided by delta t. Conservation of phi is basically, there is no problem in that if you use the scheme, because you see that your right hand side has this, say, finite difference approximation in flux form, and then if you sum it, you have 1 over delta t, sum of phi n plus 1, k, sum, over k, minus sum k phi k n will be equal to 0, because if your finite difference approximation is actually conserves phi when you use flux form, for example. So in that case, you see that conservation of phi is assured. So on the current time step, you have sum of all values of phi, and it's equals to future time step, sum of those phi. So no problem with that in case of one-step scheme, for example. However, our conservation of quadratic quantity may not work like that. So when we derived conservation of quadratic quantities, we multiplied by the scheme by phi, and of course, because let's for example we use assume that we use explicit scheme, so the right hand side, for example, is on some time step n, or maybe it can be some multi-step, one of those higher order time schemes, like can be Advanced Splash 4 scheme, second order, third order, and so on. But we have this, we assume that when in an analytical form we will multiply by phi, we just use the fact that it's from calculus rule, it's just a conservation of quadratic quantity. So this is identity. But of course, the final differences here, for example, if you use for your phi forward in time scheme, then you have divided by delta t, and you multiply by phi, let's say n, then this thing equals to phi n plus 1 minus phi n squared divided by delta t. And certainly, well, it kind of looks like this, but not quite. This is definitely the sum. So the sum of phi n squared, okay, of course not equal to sum of k phi n k phi n plus 1 k, even though right hand side maybe it's indeed equal. Let me retract that. They of course equal because right hand side equals to 0, but this is what we want. What we want is something like this, that sum of k phi k n squared equals to sum of k phi k n plus 1 squared. And of course in general it's not true for a scheme like this. This is true, but this guy does not equal to this guy. So there is some lack of conservation. Of course, still momentum can be preserved, but quadratic quantities not. I mean, not quadratic quantities in a locally, but I mean in terms of total conservation over the whole grid, the sum of all those quantities. But still, using conservation schemes that preserve quadratic quantities on the right-hand side, or the spatial derivatives, it's a good thing because quadratic quantities probably the sum, the total energy does not really change that much over from one time step to another time step. So this is approximately always true. So this can be approximately true, and it still would control all sort of not desirable behavior of scheme like due to, say, a nonlinear stability. So as people say that time scheme conserves say energy just as a kind of within kind of some truncation error, because well there is this truncation error between approximating this term. But there is one scheme that actually can preserve it exactly, and that's the only probably scheme that has this property. It's a Crank-Nicholson scheme or trapezoidal scheme in time, and that scheme is written like the following. And where time derivative is approximated as phi n plus 1, as before, phi n divided by delta t, so as before, but right hand side is actually based on a trapezoidal scheme, which is phi n plus 1 plus phi n 1/2. So instead of schemes that using phi n, for example, as if it's purely explicit scheme, or phi n plus 1 and 1, then it's purely implicit scheme. It's kind of in between. So it's still kind of implicit scheme, and you need inversion of some big matrix in order to find solution, because you still need n plus 1 value here. And this right hand side can have like all this advection operator, diffusion operator, and so on. But when you multiply now, so you define your energy now by multiplying these both equations by phi. But now if you multiply it by this, in this form, you have like 1/2 phi n plus 1 minus phi n, this guy, divided by delta t. Not 1/2. Divided by delta t, and then you multiply by this guy, 1/2 phi n plus phi n plus 1. So this is a, let me write that as trapezoidal or crank Nicholson scheme. So when you multiply, what you get, well, this is just from algebra, you know, like a minus b times a plus b equals to a squared minus b squared. So it becomes phi n plus 1 squared minus phi n squared divided by 2 delta t. So it's basically what you have, it's kinetic energy times step n plus 1 minus kinetic energy at step n divided by delta t. So it becomes exactly, you know, when you make summation of right and left hand sides, the kinetic energy of quadratic quantities will be conserved exactly if the right hand side conserves kinetic energy. Then the whole scheme would conserve kinetic energy exactly. That's why Crank-Nicholson scheme is pretty popular in modeling because of this exact conservation of energy, but of kinetic energy, but or this variance of quadratic quantities. But the problem is that it's of course implicit, so that's not so easy to solve. But in many cases, it may be worth it because if you want really some exact conservation of kinetic energy for some specific problem. So just to have this little comment on time differencing. Okay, see you.